Hello, in this video I'm going to quickly talk about the next homework, and the next homework asks you to demonstrate that vector, deck, list, set, and unordered set have some differences in the performance for various operations like pushing to the front and back, inserting, finding, and so forth. To do this, we're going to use the Google benchmark library, which is a very common library for running benchmarks. And all this is established for you already on Delin, so I'll show you a makefile. But fundamentally, you're going to make a regular function that will have to be static and void, but otherwise it's just a regular function. And then you tell the benchmark library that this is a function that it should run in a benchmark context. And it will run it many times and show you the average time it takes each time it runs it. The running part will be in this loop. So it'll measure how long, whatever's inside the loop, however long that takes. So to start this out, I'll just have, there's a little example down here. So we'll actually take this example and put it in. So this is showing how to use vector, and we're also importing random so that we can put random values inside the vector. That's going to help later when you want to use find, because you want to make sure that you're getting a lot of different kinds of scenarios where it finds it quickly, where it finds it slowly, and so forth. So we have a static void function, and then you call it whatever you want. Here's an example of pushing back in a vector. The function should receive a state variable, which is a state class from the benchmark library. And state is how it keeps track of the performance as it runs it. Now we're going to use a for loop so that it'll run many times. And inside, in this case, what we're really demonstrating is how fast does it create a vector and do a bunch of pushbacks. And we're also going to use a different number of elements for, it's going to run many benchmarks for a different number of elements. So it'll do one element and then it does multiples of 8, I think. 8 elements, 64 elements, and so forth, up to 1,000,000 elements. And that range value can be retrieved from the state with state.range position 0. So this loop runs however many times this range is defined and puts that many random elements in the vector. So what we're measuring again is how long does it take to create a vector and add a certain number of things to it. And you might imagine something else might be slower, like maybe a list might be slower for these operations. Anything you want to be outside of the timing, you can put before the for loop for the state. So if you want to set up the vector, for example, and maybe add some things to it before you just start measuring the time, just put it outside the loop. And that would allow you to say, for example, let's set up a bunch of elements. Let's put a bunch of elements in the vector. That we're not timing how long that takes. Then inside this for loop with the state, let's do a find operation, or let's do a iterator that goes through the whole vector. It's good to separate that because we want to measure, for example, how long it takes to perform a find or a sort, not really how long it takes to add things in the vector, because we have this benchmark to do that. So I'm going to leave this inside because in this case, I want to make a new vector every time. Then you have to tell the library that this function is a benchmark function. And the makefile adds the benchmark library, and on the right side here, benchmark main, that library defines the main function. So we're not going to create our own main function. As you see in the CPP file, there's no main function. When we run this, all this is from the Google tests, or the Google benchmark library. It made its own main function that performs all these operations. So what you see here is that it's running, since it's on Delin, it has 32 cores, 32 processors. Actually, I think 32 cores, 16 processors, I think. And just some stats about the CPUs. And you could ignore this warning, and it's just saying it's not going to be super accurate because the performance of the processors is changing dynamically depending on how loaded the system is. And you see it's running this function we defined with different values for the range. So here's how it goes through the range values. We're always kind of more interested in big trends. So it's doing like an exponential increase until it hits our maximum and it starts at our minimum. And it's showing how long it takes on average to run, say, this function with 4,000 elements. It takes this much time to add 4,000 elements. And over here, it says how many times it ran this version of the function. So when it's going to take longer, it's going to run it fewer times just so you're not sitting there forever. And the definition of how long or how many iterations it does is provided here. Number of iterations is determined by running the benchmark a few times, measuring the time taken, and then from that result, it sees how fast it runs when you run it just a couple times. And if it's really fast, it knows that there's going to be a lot of noise in that number, because if it's really fast, then it may be 10 nanoseconds and then 30 nanoseconds and then 12 nanoseconds and so forth, because it's also fast anyway that the processor might have some little differences based on what else is running on the system. Whereas if it takes 1,000,000 nanoseconds, that's going to be more consistent every time it checks, because since it's taking longer, the noise is kind of being washed out, because yes, the processor is doing some other things, but overall, if it's 1,000,000 nanoseconds this time and 1,000,001,000 the second time, that's all still pretty close, relatively speaking. So if it's faster benchmark, it'll run more iterations, so it's a more reliable result. And if it's slower, it'll run fewer iterations. And ultimately, it doesn't want you to have to sit there for 10 minutes while it's running, so it'll also quit pretty quickly. So these still finished pretty quickly because it decided only 10 were necessary, whereas it ran 1,000,000 of these. So that's the basic idea with the benchmark library. You can just add more of these things. Again, if you want a scenario where you want to set up something ahead of time, then just move it out. And then inside the part you're actually benchmarking might be like a find operation. Find, begin, and look for a particular, look for a random number. I don't know what's in there. It's all random anyway. So I'll just look for a random number. And we might have to import random to use, algorithm to use find. And I'd probably want to rename this find vector. It's still good to use the range in this case. You don't have to use a range if you always want to do the same thing. You could just do semicolon, but it's good to use a range here because we'll want to check how it performs for different sizes of a vector. So if the vector has all random things in it, don't measure this, but rather measure how long it takes to find something. So it's kind of linear time. Now I would expect, I haven't tried it, but I would expect that a set is going to be a lot faster for the find operation, because sets are sorted and they're actually tree structure. It's called a red-black tree. I believe that's what a set uses. I know a map uses that, and that makes the find operation probably logarithmic instead of linear like this appears to be. So you're not going to change the function every time. You're going to add a bunch of different functions and have code that does all these comparisons in the same program. So you want to show how vector, push back and front, behave, and going left to right through the whole thing with an iterator, and running find and sort. Same with the deck, same with the list. Now recall from the last video that list doesn't have the sort function from the algorithm class because it doesn't have a random iterator. Rather, you have to say list.sort. So if your list is called mylist, you'd say mylist.sort parentheses. Whereas in these cases, you call the sort function from the algorithm's include file, and it's sort with a begin and an end iterator. And then set, there's two different kinds of set. One doesn't stay ordered, and one does. And you can see how they're characteristics differ for inserting and finding and iterating. Let me know if you have any questions.